First off, what is Sierpinski's triangle? Sierpinski's triangle is a fractal, or geometric pattern repeated on multiple scales. The basic construction is to start with a large equilateral triangle, create an inner triangle by connecting the midpoints of the sides of the large triangle. This process is then repeated for the 3 outer triangles that result from that, and the 3 outer triangles that result from that, and so on.
Why is this triangle so interesting? When the number of subdivisions, n, of triangles approaches infinity, the area equals 0 while perimeter equals infinity. So though it may seem impossible, we have an infinitely long perimeter containing no area.
First, we will look at how to construct Sierpinski's triangle in Geometer's Sketchpad.
Then we will prove both area and perimeter for this triangle as n approaches infinity. How to create Sierpinski's triangle in Geometer's Sketchpad.
Select the segment tool and draw a line segment of any length.
Click on one endpoint and draw another line segment.
Create another line segment to connect the remaining endpoints.
Drag triangle vertices to fill the screen and make the triangle approximately equilateral.
We will now label the vertices. Select the text tool and beginning with the top vertice, moving counterclockwise, label A, B, and C respectively.
Deselect all points. Select all 3 sides. Go to Construct and then to Midpoints.
Label the midpoints. Beginning with the bottom midpoint and moving counterclockwise, label it D, E, and F.
Connect the midpoints using the segment tool. Then deselect everything.
Click on each midpoint and select Construct Triangle Interior.
Select points in this order: A, B, C. Go to Transform and then Iterate.
When prompted in this order, click F, B, D, so A goes to F, B goes to B, and C goes to D.
Click on the structure box and then Add New Map.
When prompted in this order, click E, D, C, so A goes to E, B goes to D, and C goes to C.
Click on the structure box and then Add New Map.
When prompted in this order, click A, F, E. Then click Iterate. You have now completed Sierpinski's triangle.
This is the explanation on how to find the perimeter of Sierpinski's triangle. After the nth iteration, the general formula for the perimeter is P of n equals 3/2 to the n power times 3. Each time we iterate, we increase the number of triangles by a factor of 3, each with a perimeter of half the previous triangle's perimeter. In other words, we increase the total perimeter each time by a factor of 3/2. Perimeter examples, assuming each side equals 1 unit, the original triangle has a perimeter of 3 units. After the first iteration, the perimeter is 3/2 to the first power times 3. After the second iteration, the perimeter is 3/2 squared times 3. After the third iteration, the perimeter is 3/2 cubed times 3. See a pattern? Taking the limit of the perimeter equation, since 3/2 is greater than 1, the equation grows towards infinity as n gets large. Thus the perimeter of the infinite Sierpinski triangle is infinite.
Here we are going to look at the proof for the area of Sierpinski's triangle. First, we find the area of the original triangle, assuming all sides equal 1. We see the area is the square root of 3 over 4. For the first iteration, we subtract the area of the middle white triangle, which we see as 1/4 the area of the original triangle, from the square root of 3 over 4. For the second iteration, we are subtracting the area of the smaller white triangles from our previous formula for A1. We see the smaller white triangles account for 3/16 the area of the whole original triangle. We get this formula for A2. For the third iteration, we are subtracting the area of the smallest white triangles, which are 9/64, or 3 squared over 4 squared, of the area of the original triangle. We can now see a pattern for this formula. AN shows what area equals after n iterations. We want to simplify this formula before we take the limit as n goes to infinity. The first step is to multiply the numerator and denominator by 3, which will allow you to simplify the exponents. Then pull the constants out in front of the sum. To simplify farther, we need to make I equals 0 so we can use the formula for a geometric series to solve for the sum. We do this by setting I equal to 0 and subtracting 1 from the entire sum. Since the sum is now a geometric series, we know the sum equals 1 over 1 minus r, where in our case, r equals 3/4. Simplified, this is what we get for AN. Since the 3's cancel out, we are left with the square root of 3 over 4 minus the square root of 3 over 4 equals 0. Taking the limit of 0 as n goes to infinity is 0.